Which of the following is not an assumption of the kinetic molecular theory of ideal gases? And the answer is D. There are intermolecular forces between the gas particles. That is not an assumption of the theory. The first three choices, in fact, are the three main assumptions of the kinetic molecular theory. And the last one actually contradicts one of these three assumptions. It contradicts choice C, the third main assumption of the kinetic molecular theory. So it can't be D. Let's take a look at the kinetic molecular theory and see where this one actually fits in and how it contradicts the third main assumption. The kinetic molecular theory models a gas as a collection of particles in constant motion. Here's our picture. Gas particles are far apart from one another, and you can compare the picture of a gas with that of a liquid and solid. Solid particles are very close together and ordered. Liquid particles are also close together, but not as ordered because they're moving around one another. Gas particles are also moving around, but gases fill up their container, and so there's a lot of space between the particles. So that's our picture. And the three main assumptions of the kinetic molecular theory are as follows. First, the particle size is negligibly small. The gas particles occupy hardly any volume compared with the volume of the container. As you can see over here, our picture again, these arrows represent the motion of the gas particles, and the length of the arrow tells you how fast it's moving. So the gas particles themselves, they're tiny compared to the actual space that they occupy. And the theory says that you can neglect their size. So that's our first assumption. The gas particles are too small to take into account. Assumption number 2 says the average kinetic energy of the particles is proportional to the temperature. Kinetic energy in physics is defined as 1/2 times the mass times velocity squared. Kinetic energy is energy of motion, and gas particles are constantly moving around, so we say they have kinetic energy. We say they are moving. Now, the faster they're moving, the more kinetic energy they have, and vice versa. The more kinetic energy the gas particles have, the faster they're moving. Now, the second main assumption says that the average kinetic energy, you can kind of think of that as like the average amount of motion. The average kinetic energy of the particles is proportional to the temperature. In other words, if the temperature is doubled, their average kinetic energy doubles. And if the temperature triples, then so does the average kinetic energy. It's proportional to the temperature. So on the one hand, kinetic energy equals 1/2 mv squared, according to the definition of kinetic energy from physics. And on the other hand, it's proportional to the temperature. The constant of proportionality is actually 3/2 times the gas constant R. So this is the constant of proportionality. Since the kinetic energy equals this on the right, and it also is proportional to the temperature, so therefore equals that on the left, we can set these two equal to each other and actually derive from that the equation for the root mean square velocity of a gas particle. The velocity of a gas particle equals the square root of 3 times the gas constant R times the temperature over the molar mass. And you can see how plugging in larger temperatures result with larger root mean square velocities. So hotter temperatures, the gas particles are moving faster. Now, in our picture over here, we see some of the gas particles moving pretty quickly. Other ones, like this one, are moving pretty slowly, but there's an average speed. That's the second main assumption. It's proportional to the temperature. Now, the third assumption says collisions between the particles or the wall are perfectly elastic. In other words, if a particle bounces off the wall of its container, it ricochets off and keeps all of its momentum. It doesn't slow down because of the collision. There's no stickiness. It doesn't collide with the wall and kind of stick to it and therefore move more slowly. No, it just moves off with the same speed that it had before the collision. Perfectly elastic. And that happens when two particles collide with each other as well. The conservation of momentum is there, and the particles don't really slow down, and that's what a perfectly elastic collision is. Now, imagine, say, these two particles, which are heading towards each other and are about to collide. If there are intermolecular forces between the particles, then as they approach one another, they would actually interact and want to stick together, and after the collision, they may not be moving as quickly as they did before, and that's because of that stickiness, that intermolecular interaction. So intermolecular interactions between the particles cause collisions to not be elastic. Now, we do know that there are intermolecular interactions between particles, but in a gas, the particles are moving pretty quickly and the intermolecular interactions are not as important. So we assume that in this theory, but it is an assumption and it is maybe a little bit of an imperfection in the theory. So it's assumed that the collisions are perfectly elastic, even though we know that that's not quite the case. And so you can see how choice D, which says there are intermolecular interaction forces between the gas particles, actually conflicts with the third main assumption of the theory. Now, taking into account intermolecular forces and also taking into account the actual size of the gas particles, in other words, if we get rid of assumptions 1 and 3, that is how we can model real gases. And that's how van der Waals constructed the van der Waals equation, which models real gases. But that's another story, and the answer here is D, and hopefully you see how that's conflicting one of the three main assumptions of the theory.